Okay. Yeah. Hello. Okay. Hi. I'm Yeet. I was working on this game called ZheroTag, which is a game that's based on zero knowledge proofs and something called multi-party computation. I personally really like the instant gratification monkey, so we will be straight up starting with the game itself. So let's play. So it's a very it's a very basic setup. You just have a white king and a black king on a chessboard, and it's 6x6. And the kings move as usual in a usual chess game. And the goal is to just in a normal game. Goal is to capture the other pieces, but in this case, you can capture the other king. And the main difference between chess and ZheroTag is that in ZheroTag, you can only see the pieces, the squares around your piece. So in this case, the kings can move to the. Wait, I'm hearing the background noise.
Oh, Marcia is just sharing his repo.
Well, that was a recursion. Wait. Okay. Can you see the presentation again?
Yes.
Okay. And in this case, the main difference is that the kings can only see the squares that they're in and the squares that they can move to. And so in this game, what the two sides are basically doing is to sort of roam around in a fog of war, trying to find the other person. But obviously, to win, you should stumble upon that person in such a way that their move brings them to you first, because otherwise you get captured. And so, okay, let's play a example game. Okay, good luck, everyone. So in the first step, white makes a move, doesn't see anyone, and then black makes a move, doesn't see anyone, and just goes on and on and on until white makes the mistake. Again, it doesn't know at all where black is. White makes the mistake of stepping into the black's vicinity. And at this point, as you can see, the black king appeared on the white's view, and the white king appeared on the black's view. So whereas in these previous moves, we don't really see an update, we actually need to check, we need to update each board after every step. And obviously, as the next step, black now sees the white king, and then it captures to win the game. And so I guess at this point, I need to mention why this game was a game that was worth implementing. I actually started in late summer with this game, thinking about it. I didn't know actually if it was really possible to make this game. I was looking at some contracts for Battleship, the game where the two sides have a ship configuration and they fire missiles to each other. And I guess it's more like a classical zero knowledge proof game, and the game goes as follows. Everyone has their own private game state, again, which is the ship configuration, and they fire their shots publicly. So you declare the coordinate that you want to attack, and your opponent takes that public attack and passes their private game state, and then they output the zero knowledge circuit saying you hit or you missed. And if it's a hit, you go again. If it's a miss, it's the other person's turn. But that's roughly how the game progresses. And it turns out the game can be implemented by using only zero knowledge proofs. You don't need any fancier things like multi-party computation that I will need here. And if you think about it, the reason why zero knowledge proofs are enough is that there's sort of two games happening at the same time in Battleship. One game is played completely on your board with your private game state with public attacks on it. And the second parallel game is the game played on the other board with their private game state ship configuration and your public attacks. But in this case, if you think about it, it's not two separate boards that can be updated independently of each other. In ZheroTag, you have the same board and the private game states are operating in sort of the same space. And so it's no longer enough to say, okay, I made a move, and here's proof that it was a valid move. Here's proof that my king just moved by 1 square. But in this case, in ZheroTag, you should also update both boards, like I said. And so yeah, for several weeks, including the beginning of the program, I was trying to make a protocol that would make it work. But one important detail is that it is almost trivial to implement this game if you have a trusted third party. I got these screenshots from chess.com, and even if you go to chess.com, you can check the variants page, and there's a variant called Fog of War, which is pretty much the exact same thing as ZheroTag, but obviously with more pieces and more like a regular chess. But that the main idea is the same. But in that case, again, chess.com is a trusted third party that both sides trust. And roughly how this works is the following. Okay, wait, I have different emojis than what I had in Firefox. But if it's assuming it's White's turn, what White does is it sends its next move to trusted third party. And the trusted third party has more like a god view of the board. It can see where everyone is. And so it makes the regular calculations and sends both white and black where their pieces are and which squares they can see. And so after only 3 sort of communications, you can update both boards. It's very straightforward. But again, the catch is that you need to trust the third party. And the whole challenge of ZheroTag was to have this game implemented using a completely P2P system. And after some time, again, like I said, we did find a solution, but let me just repeat some constraints. They can only see the squares around their king. And again, both boards need to be updated after each move. And one thing that I also need to mention is players are malicious. So you can't just say, okay, this is P2P, I will be sending your computer all the information that it needs. I'll be sharing my position, I'll be sharing my everything, and the computer will just use that information to compute what you as a person should see. We can't really say that because there is no guarantee that the opponent as a malicious person will just use the message that you send directly, and it doesn't have to rely on the client-side software. And also, the players happen to be rational people who trust math, and so we have all the options you can see there. And it turns out there's a solution using zero-knowledge proofs and something called private set intersection, which is a concept that I learned towards the beginning of the program, I believe. The idea is very simple. You have an n number of parties. For simplicity, you can say you have 2 parties, and they have a private set that they don't want others to see. And they want to calculate the intersection. Let's just say there's a public good in both of them knowing what the intersection is. And we will later apply this to our game. But currently, I'm just trying to stay a bit theoretical. And the idea with these protocols is that while calculating the intersection, they don't want the other party to learn the values that are not in the intersection. And you might ask, how is this even possible? Can we do something other than closing our eyes? It turns out you need to use commutative operations just in case. It just means that changing the order of the operands does not change the outcome, just like how in multiplication a times b is equal to b times a. And each private set intersection protocol has at least a few steps that roughly follow this pattern. You have a private value. Let's say you can call it A for yourself for player 1, and player B has another private value B, and they apply the values to their own sets, and then they exchange these values, and for example, player 1 applies A to the values that it receives, and player B applies B to the values it received, and then they compare if any of the outputs are the same. And so essentially what it boils down is, if we had the same value initially, then A times B is equal to B times A. So we had the same value. And another important point is that these operations that we're doing with these sets is not as simple as multiplication. So if you know the outputs, you can't calculate what the inputs were. So for example, if we were given that A times B is equal to 6, you have only so many options. It's either 2, 3, or 1, 6. But we have a more complicated setup, so they can't really calculate the values if it's not in the intersection. And how do we? I guess at this point I can ask if there are any questions, just conceptually. Again, I can't see anyone, so.
I think no questions at this moment.
Okay. So with ZheroTag, the application is very straightforward. The most efficient protocol that I could find uses PSI 2 times, and each PSI is responsible for updating only one of the boards. So let's say we're trying to update White's board. White just made a move, and for our first set, we need to have the White King's neighbors. And for the second one, we have the Black King's position. And the first PSI reveals the position of the Black piece to the White King only if it is in the neighborhood of the White King. And obviously, we need to be using zero knowledge proofs on the side to prove that the values that we put into the PSI are actually the values that are supposed to be there. Because if you don't have the zero knowledge proof checks, you can just ask them to, I'm not sure if you can see my cursor, but you can just give them values like this, or stuff like that, random positions on the board, and you can sort of try to guess the position, which will be cheating. And so we have zero knowledge proofs on the side, and we have digital signatures as well. There's a signature class in Snarky.js that I used, and also the private keys and public keys for signatures and stuff. And for just going back to the PSI protocol for ZheroTag, to update Black's board, you literally do the exact same thing, but just for Black now. And yeah, that's pretty much it. You don't have anything else. And something that I should mention here is that these protocols are so delicate that I really have to be careful with every single step. For example, let's say the Black King was at the very corner. In that case, you have only 3 neighbors where the Black King can see. But again, I'm not sure if you can see. but the first square is this one, the second square is this one, and third square is this one. And so if the black king sends only 3 values in its PSI, then it sort of leaks some information to the white king, right? Because it implies that the black king is at a corner. And so, I also always had to think about these edge cases to make sure that nothing was wrong. And the implementation follows this specific gameplay. White makes a move, white starts PSI 1, and then sends its first set to black. And then black responds to the PSI 1, meaning it exponentiates the values using its own private value. And then with its reply to PSI 1, it starts PSI 2 at the same time for communication efficiency. So you have that on the white side now. And white, at this point, can update its board because it has completed PSI 1. And it needs to reply to PSI 2 for black to complete its board. So it does that. And once black receives the third and last communication, it is now ready to update its own board, and the cycle just repeats and repeats. And all this process is completely off-chain. I made it intentionally so that people would not need to think about the gas fees and network congestion or anything like that. And I just wanted to show that blockchains can be used as sort of like an arbitrage layer, which is related to the next slide, which I will talk in a minute. But let me just explain how it works off-chain. What you do is the functions are public. So I have a smart contract that you can use to update the protocol state, to create the PSI packet, the PSI packets. These things are public, but the players use these smart contracts, and they produce the zk proofs and the outputs. Instead of sending them to the chain, they just send the results to the other person using a P2P channel. And if there is no dispute, then you can stay completely off-chain. You have also, like I said before, you have signatures, electronic signature, digital key signatures at every step. And so everything is recorded and signed. And if everyone is behaving well, then you can stay off-chain. But if there's a dispute, that's when you need the arbitrator smart contract, which I didn't have to work on. But here's like a conceptual idea as to how it would work. It is completely separate from ZheroTag. I imagine it to be just a separate utility that other applications can use. You can, for example, use it to prove that it's your brother's turn to go to the grocery or something. But for ZheroTag, what you do is I call these things tickets. When you want to create a new utility for your application through this arbitrator, you go to the contract and say, here are 3 functions. Function 1 is to prove that someone else in the network must be calling function 2. So this is like the function 1 is what the forcer is calling to force the forcee to call function 2. Again, this is generalized, but I'll be applying this to ZheroTag later. And function 2 is called by the forcee as a reply to this force move. And function number 3 is for, again, the forcee, but the forcee calls function 3 only when it thinks that it has at least it has proof that the first player didn't have the right to force the foresee to call function 2. This might have been a bit of a complicated process, but for ZheroTag, it's very straightforward. If, let's say, the opponent is not replying to you, then you call function 1, which is a function that the ZheroTag administrators, which is me, has submitted to the arbitrator. You call that function and say, here's proof that if you were playing this game, and because you have every step signed by the other person, you can prove that they were in this game. We have played this game so far. We have made these moves, and this is my turn, and I want my opponent to reply. And the arbitrator starts a timer. It doesn't matter how much time the other person should have. You can define it in the game settings or stuff. And the opponent is given this time to reply. If they were actually just ghosting, then they must reply in that time, because otherwise they lose the game. If they reply in time, the game continues on and on and on. And there's always the option to call function 3, which is when the opponent thinks that you are not right to do that. Let's say you might ask, when can this even happen if everything is signed and stuff? Let's say I'm playing a game with Regina, and we have played for 100 times so far this game. And if I just go to this smart contract randomly and say, here is our game number 10, and this is my move, I want Regina to reply. But then in this case, Regina can call function 3 and say, here's proof that we have already played 100 games and all of them have already finished. And in that case, I will be punished for using the arbitrator. What else do I need to talk about? I can show you some of the code. Let me pull up the... Can you see my Visual Studio screen?
Yes.
Okay, if I have 2 minutes, just very quickly, the main two files are the protocol state and the game state. Game state keeps track of what the player addresses are, the situation of the boards, and whose turn it is. And the protocol state keeps track of the protocol steps. Like I said, you have like a 3-step process after every move to update both boards. That's how we keep track of them. And the players hold the move methods, the reply to move methods, and I didn't have a better name for it, reply to move, to complete the entire process. And at the end, it just loops around. And then the other person starts with move again.